What's up, everybody? Hope you're all doing fine. Elon Musk has just joined Manchester United.
What feels right about this move at this point in your career and your life?
I think it's the best decision that I have made it, and it's right on a point that I am so happy and glad, and I want to carry on again to make history, to try to help Manchester to achieve great results, to win trophies, and I'm one of them to help the team to win great things.
As you may have noticed, this isn't Elon Musk, but a deepfake of an original video by Manchester United where Cristiano Ronaldo talks about his most recent move to the club. This deepfake, and more precisely FaceSwap, has been done using the SimSwap framework, which was presented in this paper, SimSwap, an efficient framework for high fidelity face swapping by Ren Wang Chen, Huang Hong Chen, Bing Ni, and Yang Hao Jie. In this playlist, we are gonna do a detailed paper review of this SimSwap paper, and then you'll learn how to create your own deepfakes using this collab notebook provided by the authors of the paper. And before we dive deep into the subject matter, don't forget to please subscribe and click on the notification button so that you keep having high quality content like this. SimSwap, which actually stands for Simple Swap, is a framework which provides generalized and high fidelity face swapping. If you're new to face swapping, here's what's about. Here we have this source image. So generally we'll have a source image and then a target image. Now what happens here is we want to swap the faces in the source and target images. And the way it's done is by taking this face from the source image right here and then transferring it to the target image face, such that the attributes of the target image, like the expression, pose, and even the gaze, is maintained, but we'll have a new face right here. So we have this identity which is being transferred from this source image to the target image to provide now this output, the result where the source and target images or source and target faces have been swapped. Now this technology could be used or is being used in the movie industry, as we could now have a movie where we have this actor right here and then we recreate that movie now with Djokovic being the actor. So we see how we've transferred this identity to this target image right here while preserving the target image attributes. And we have seen this in this example previously where we have this source image of Elon Musk, which has been transferred to this video where Manchester United presents Cristiano Ronaldo, and then we have this output which appears like it was Elon Musk who was actually in this video by Manchester United. Compared to other methods, the Simple Swap framework does better at transferring the identity from the source to the target while maintaining the target attributes. We'll see right here how this previous method, Defects, which is a very popular method, produces this kind of output where some parts of the source image, or rather some attributes of the source image, are still being transferred to this output right here, which is an unwanted transfer, since all we want to do is just transfer the identity from the source to the target. Now with the SimSwap, we'll see how it performs better than the Defects method in this example, where the attributes of the target is preserved and we have this great face swapped output right here. And another interesting point to note right here is we are having this kind of results without training on this particular image, unlike a method like the deepfakes where each time we want to create a face swap we need to train on the source and the target image. And the way this works is we pass in the source and the target image in an encoder. This encoder permits us to extract ID information or identity information about the source and the target images, and also attribute information. Then that said, we then pass this information into the two separate decoders. One decoder for the source image and the other for the target image. And then the encoder and the two decoders are trained such that we are able to retrieve the source image, which is this one right here, the source image, and the target image respectively in the output. And then after training this whole network, what we now do is, in order to create a deepfakes or in order to do the face swapping, we'll take this target image and then pass it as if it were a source image. So we'll pass it in here, and then all this information goes into the source decoder. So instead of having this image pass into the target decoder, we now pass this target image into this path right up to the source decoder. And so since this decoder has already been trained to produce an output with the identity of the source, we have an outputted face swap or an output face swapped image wherein we have the ID of the source birth with the attributes of the target. And so clearly, each time we want to create a face swap, we will need to go through the training and then pass this target into this decoder right here. And so this doesn't permit us to have a generalized model in which after training we could just simply pass in the source and target information and have the faces swapped without necessarily having to go through a training process. What makes the simple swap method powerful is the fact that it permits us to generalize to arbitrary identities without necessarily having to train on these arbitrary identities before doing the face swap. And then it also provides a way to reliably preserve the attributes of the target. In order to achieve generalization, the SimSwap method tries to separate the identity information from the decoder, because having this information in the decoder here or starting the decoder weights simply means each time we want to do a face swap, this decoder will only output a single identity, which is that on which it was trained on. But what we want to build now is a model on which we could do face swaps or output images with identities different from the identity of the image on which the model was trained on. Here we have the SimSwaps framework, which takes in a target image and your source image and then outputs this swapped image. Recall that the aim of this task of this model is to take this target with an ID, that's IDT, ID target, attribute target, and then the source, IDS, ID source, attribute source, and then come up with this output which has IDS and then attribute T. But now with a simpler and more generalizable model in which we now have between the encoder and the decoder this ID injection module, which now is responsible for passing in the source's ID into this output in such a way that when given two inputs, that's a target and a source at test time, the model simply gives us this type of output without having to train this tool. And here is how it is achieved. We have this target image right here and then the encoder which outputs some features. So we have what call this features. We have features right here as denoted in the paper, but these features contain both ID and attribute information. And so what we do is we include this ID loss right here which permits the model modify its weights such that once given this output, this ID extractor produces a vector which is similar to this vector produced when this ID extractor takes as input the source image. So in fact, what we're saying is we're having this two ID extractors and we're making sure that their outputs are similar. And making sure the outputs are similar simply means we're making sure that the FaceSwap output ID is similar to that of the source image ID. And hence, we are able to transfer the source's ID into this FaceSwap output. And thanks to this ID loss, or thanks to the system in which we're trying to minimize the difference between these two vectors, the model learns how to differentiate which parts of this feature output have to be modified or not. Note that the ID injection module is made of two parts. That's the ID extractor and the embedding, which is like an ID injector. Right here we could see these features getting in, the features from here getting in, and then we have this ID block. This is an ID block, so here we have this ID blocks, and then the others use 9 of these ID blocks to ensure that the ID information from the source is transferred reliably into this target such that we have this type of output. These ID blocks have a ResNet-like structure, and then they use the adaptive instance normalization instead of the batch normalization. So we have this right here. And so the whole network is trained on many different triplets of target image, source image, and swapped image, wherein our ID injection module is responsible for extracting and injecting the ID information into the features or into the target features from the source image, and the decoder now learns how to produce those swapped outputs with the source's ID regardless of whether we're having as inputs a particular source target pair. And with this, we're able to come up with a generalizable model in which the next time we want to have this swap, all we need to do is to input a source, input a target, and then we have this output. The next important role of this framework is that of preserving the attributes of the target. As you'd see, for now, we had modified, or we had included this ID loss, which permits us modify the weights or train this whole model such that we're able to come up with outputs whose IDs are same as that of the source image. But the problem with this approach is that given we're doing modifications on the whole feature right here, this model may tend to overfit by paying much attention on the ID restoration part and not doing much to ensure that the target's attributes are maintained. And so to solve this problem, we have this discriminator network right here, which takes in the target image and the result image. So it takes in this output and then this target, with the aim of ensuring that the attributes and the target are restored on the resultant image. To ensure this, we use the weak feature matching loss right here. Now let's explain why we need to use a weak feature matching loss. Firstly, we try to ensure that we try to match these features with these features from the resultant image, so that our output at resultant image has attributes similar to that of the target image. But the reason why we actually need a weak feature matching loss is because of the way confnets work. Now, in a usual confnet, if we have this image, let's say we input this image, in the very first layers, let's say we have the first layers, and then we go up to the very last layers. In this layers here, we have mostly the texture information, which in fact is just low level data, while this final layers right here contain more of high level semantic information. And so if we try to make sure, or if we have a loss where we're trying to ensure that the low level features in the target image and the results in image are matching, then we'll tend to have the ID of this target image being passed on to the output image. And so to avoid this, we'll only want to work with this high level features which contain mostly semantic information, which is not so much related to the ID of the target image. And hence we could, with this deeper layers, only ensure that the attributes are transferred from the target to the output without much transfer of the ID information. And now we have this two models, this one and this, which have been trained adversarially to ensure that the ID information is passed to the output and the attributes passed to the output in a reliable manner. Here the authors define the weak feature matching loss, which has same formula as a usual feature matching loss. And then they define the overall loss function. Let's get back. We have this overall loss function right here, made of the ID loss, which we've seen already, a reconstruction loss, which ensures that if the source face and the target face are from the same identity, the generated result should actually look the same as that of the target face. So some sort of regularization loss. And then we move on to the adversarial loss with gradient penalty, which ensures that this generated resulting image is of high quality. Now, if you're not versed with the GANs, that's, you see here we have this adversarial loss right here, the generative adversarial networks. You could check on our videos in the generative modeling playlist. Then finally we have this weak feature matching loss, which we've seen already. And then the overall loss is kind of like the weighted sum of all these different losses. For the implementation details, here they choose a large face data set, VGG face, as a training set. And then they take away all images with size smaller than 250 by 250. They align and crop the images to a standard position with size 224 by 224. And then for the identity extraction, they use a pre-trained face recognition model that is ArcFace. They train the network using an Adam optimizer with beta 1 equals 0, beta 2 equals 0.999. And then while training, they train one batch for image pairs with the same identity and another batch for image pairs with different identities alternately. This training is done for more than 500 epochs. Let's now go ahead and look at some qualitative face swapping results. As you could see, we have a source, like the sources, and then we have the targets. Then we have our results here. So we have this image source and then this image target, and then we have this result. We could see how the SimSwap model is performing quite well. And then comparing with other methods, we see that the SimSwap again outperformed the others like the Defects and then the face shifter method. And as you could see, the SimSwap framework does better at preserving the attributes of the target image while ensuring that the identity of the source is being transferred to the target image. If you could take a look at this example, notice the lip of this woman. We have this, notice how this is maintained, see this attribute. And then for this other methods as the defects and then the face shifter, we have this kind of outputs instead. So that's it. Looking here too, you will notice that the SimSwap does a better job at preserving these attributes right here as compared to this other method. With other methods, we also have areas like this. See this kind of error right here. See this right here. And then with this other example, you could see how this smiling expression from here, from the source, is transferred into the output, which isn't exactly what we want, since all we want to do is just transfer the identity and not the expression from the source. You see that the SimSwap does a better job, maintains the same attributes while transferring the identity from the source to the output. Then we also have this other table comparing the defects, phase shifter, and then different versions of the SimSwap method. Here this stands for the original feature matching, that is SimSwap with feature matching, and then SimSwap without feature matching, so you have no feature matching right here. We find that when there is no feature matching, the ID retrieval is improved, though it doesn't get to the value of the phase shifter, but nonetheless the posture attribute reduces in value when we're using the feature matching. Note that here higher means better and here lower means better. And then this table, the authors compare the different feature matching terms and the ID weights. Now recall that in the formula, in this last formula right here, we had the feature matching weights, lambda, which they set to 10. And in this table, they obtain different results for different values of lambda. In conclusion, the SimSwap is an efficient framework aiming for generalizing high fidelity phase swapping, and the IIM, that's an ID injection model, helps transfer the identity information at feature level and extends the identity specific phase swapping into an arbitrary phase swapping model, since the decoder is no longer responsible for restoring the source's ID in the final output image. And then we also have the weak feature matching loss, which helps maintain or preserve the attributes from the target image. And now we have a framework which is capable of producing visually appealing phase swaps without even training at test time. And so now all you need is the source image, the target image, and you have your output. Thank you for coming this far. In our next video, we are going to use the collab notebook provided by the authors of this paper to create deepfakes in a few minutes. Take care and see you next time.